Hi everyone. Welcome back to Dave's Math Channel. I'm your host David Tare. Today I'm gonna give an interesting problem involving complex numbers, complex analysis. So in particular, I'm going to show you how you can use complex analysis to find a buried treasure. And this is kind of an amusing problem. The mathematician who came up with this problem was George Gamow. He was a pretty famous mathematician and physicist. He wrote a book called 1, 2, 3 Infinity, which I read a long time ago. I think I have it somewhere here at home. And I think he wrote this back in 1940. But I'll describe the problem that he proposed, and I think it's a very clever problem. So he actually put this in his book, and he actually made it kind of look like it was real. So he said, and I think when I first read this book, I thought it was real. He said that there was a note about a buried treasure, and I'll just read what he said. The note said. So first it said, this isn't the whole note, but first it said how to get to this island. So it says there's a buried treasure on some desert island, and it gave the location, exact location, latitude, and longitude, so that somebody could go and sail there and find the island, and then follow these instructions and dig for the buried treasure because it gave exact instructions on where to find it. So here's what the instructions said, go to the gallows pole. So there's a gallows pole on this island. You can kind of see it. I think it's marked with a gamma. But they said, go to the gallows pole and walk directly to the pine tree, counting your paces as you do. So you'll see that there's two trees in this picture, too. There's an oak tree on the left and a pine tree on the right. And Gamma also said that those weren't the real types of trees on this island because you probably wouldn't find an oak tree and a pine tree on a desert island. But he said that that's what he was translating into different kind of trees. So anyway, so that's the first instruction. I'll start at the beginning again. So it says, go to the gallows and walk directly to the pine tree, counting your paces as you do. Once there, turn 90 degrees to the left and walk the same number of paces away from the tree. Put a stick in the ground at that point. Go back to the gallows and walk to the oak tree, counting your paces as you go. Turn 90 degrees to the right this time and walk from the tree the same number of paces. Put a stake in the ground at this point also. The treasure is buried exactly halfway between these stakes. So that's very specific instructions. And then what Gamma goes on, he says that these guys actually found this note and they went to look for this treasure. They went to the island, but the problem was when they got to the island, there was no gallows pole. I guess the gallows pole had eroded away, or maybe it fell down. This I guess this note was made a long time ago, and the gallows pole was no longer there. So then the guys who were looking for the treasure just gave up because they didn't know how to find it. They kind of started digging haphazardly around the place and they never found the treasure. They went home empty-handed. So that's what he says. And, when I read this, I actually believe this was true. I'm pretty gullible, I guess. But he just made up this problem. I think it's an amusing problem. But anyway, what he also said was that you can actually use complex analysis to solve this problem. And it turns out that you don't need to know where the gallows pole was. So I'll explain how you can do that. So here's the way I'm solving the problem. This is also the way Gamma describes the solution. So you set up what's called an Argon diagram. It's just another word for the complex plane. And you can put the oak tree and the pine tree. Those are sort of just two arbitrary points on this island. So you might as well set them up in a nice way. So we put the oak tree, we call that O in this picture. O equals -1. So we set up the oak tree to be 1 unit to the left of the origin of the Argon diagram. And then similarly, we put the pine tree 1 unit to the right. So O is -1 and P is 1. And then what you do is you just follow these instructions. You represent everything as a complex number. So we write gamma for the gallows pole, which is kind of clever because the gallows pole looks sort of like the letter gamma. So you let gamma just be A plus IB. We don't know what A and B are. They're arbitrary real numbers, but we don't know what they are. They're unknown. But that's okay. We just represent gamma as this arbitrary complex number. And now what we have to do is we have to calculate the coordinates of where we're putting our stakes, and we call those points A and B. So A is the complex number corresponding to the location of the first stake, and B is a complex number corresponding to the location of the second stake, and X marks the spot. That's where the buried treasure is. X is the midpoint of A and B. So that's what we have to do. We have to find the coordinates. So ultimately, we have to find the coordinates of X. So first we locate A. That's not too hard. I mean, so they say that A, you're walking, you walked a certain number of paces from the pine tree to the gallows pole. And that you can think of that path as a complex number. That's just gamma minus 1. Since P is 1, the complex number corresponding to, if you think of a complex number as a vector, that vector is just the vector going from the pine tree, P, to the gallows pole. And if you want to write that as a complex number, it's just gamma minus 1, which is A minus 1 plus IB. And then, what did I write? Yeah. A minus 1 plus IB. That's gamma minus 1, but now we have to multiply by minus I because we're turning 90 degrees to the left. That means we're turning 90 degrees clockwise, and when you multiply, this is a fact I think I mentioned. I did a video on complex numbers earlier, and when you multiply a complex number by minus I, that corresponds to rotating that complex number 90 degrees to the right. So that's all that means. When you're not rotating a complex number 90 degrees to the right, you're really just multiplying that by minus I. You'll have to trust me on that if you don't know the math, but it's true. Just take my word for that. So that's what we do. A is minus I times gamma minus 1, and when you work out the coordinates, that works out to be B plus I times 1 minus A. That is capital A represented as a complex number. So we've located our first stake. And it still depends on A and B. It still depends on the location of the gallows pole. And then we do the same thing for the point B, capital B. So notice that now we have the vector B plus 1 because the oak tree is located at minus 1 on the x-axis. So we really have B minus 1, which is the same as B plus 1. So B plus 1, by the same reasoning we did before, this time we had to go 90 degrees to the right, which means that the B plus 1 is now I times the difference gamma plus 1. Remember, gamma plus 1 is the vector corresponding to the starting at the oak tree and ending up at the gallows pole. So we multiply that by I and we get B plus 1. So you can solve for B plus 1. I did it here. You end up with minus little b plus I times 1 plus little a. And now you just have to add 1 to that to get b. So you get b equals minus 1 minus b plus I times 1 plus a. Now we have to locate the treasure. So remember, the treasure is the midpoint of a and b. Well, that's just capital A plus capital B over 2. And when you work that out, you get something pretty remarkable happening here. You get little a and little b cancel from this equation. Notice you have I worked out the details in this calculation. You get, for the real component, you get 1 plus b minus 1 minus b. That all cancels. There's no real component. And then the imaginary component is 1 minus a plus 1 plus a. This one doesn't cancel. You're left with 2i. So when you're done, you get 2i over 2, which is equal to I. That's where the buried treasure is located. It's located the way we set up our coordinates. It's located at x equals I in the complex plane, and that's easy to find. You didn't have to know where the gallows pole is. It's pretty easy. I mean, notice that the oak tree, the pine tree, and the treasure make a isosceles right triangle. So all you really have to do here is you can go sort of halfway between the oak tree and the pine tree, and then you go perpendicular. You just go perpendicular the line between them, the same distance. That's where your treasure is. Pretty amazing. So that's how you could use complex analysis to find a buried treasure. Unfortunately, the story wasn't true. I kind of thought it was when I first read his book, and I thought maybe I could go look for it. But of course, he didn't give the latitude and longitude, and I don't have the equipment to search for a buried treasure, and it was a fictional story anyway. So I'm glad I didn't waste my time doing that. But I think it's an entertaining problem. I hope you enjoyed it too. And that's my talk for today. Thank you for watching. Long live math, and I'll see you guys next time. Bye.